Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you've chosen to join us today. Let's go inside. The lecture's about to begin.
All right, let's quiet down. I see you're all comfortably fed and drunk today in terms of coffee. Welcome again to our distinguished lecture series. Today we have a very special person, Dr. Paul Green. He's one of those almost unsung heroes who's accomplished so many things in his life, it's almost embarrassing for me to go through this, but of course I will. There's no stopping me. And the question is, for someone like himself, again, what is it that got him into the area, motivated him to do the things he's done, and indeed, what along the way molded the paths he took. So I want to go into some of that. So we'll go way back again to his upbringing. Paul had the privilege, if you will, of having as he says, a famous father of the same name as Paul Green. His father was a Pulitzer Prize playwright. He grew up in North Carolina, and as Paul says, it's awfully difficult to follow in the footsteps of your father, especially if you don't have any talent in writing, as was his case, which he considered a benefit, so he could distance himself as far as he could from the field in which his father was a success. Paul, in fact, felt very competitive, and as he said, he wanted to outdo the old man. So the question is to find the area to do it in. Well, Paul's expertise was in tinkering, in playing with the mechanical and electrical things, and trying to basically satisfy his curiosity, how to build things with his own hands. His early career was somewhat unnoteworthy. And he went through college, considered himself an average at best student, but on the way, he played boogie-woogie piano and managed to chase girls. He blossomed when he married in his late 20s. And he went from North Carolina, some undistinguished school there, to MIT. And he went there to get what some of you may know as the EE degree. It's a degree between the master's degree and the PhD. It's one without a dissertation requirement. And the trick is once you're there to get into the PhD program, which means passing the then infamous PhD qualifying exam, which was an enormously narrow filter. You know, it was an N-way merge, one out, N in. And N was a big number. Paul, of course, passed that exam, got his PhD, and learned how to do a number of things in that experience, which then began to show themselves as he moved into his early career. One impressive thing about his degree, he actually had circuit diagrams in his dissertation, which was not typically the case at MIT. It was practical as well as analytical. And what he did at Lincoln Laboratory, which had just been formed shortly after he got a degree, was to develop what was not yet known as a spread spectrum system. His was one of the first spread spectrum systems. He and Bill Davenport from Lincoln Laboratory put together a group to do what they called noise modulation. Noise as in spread spectrum. At the same time, Bob Fano from MIT and Lincoln Labs was putting together another spread spectrum system for radar. And both groups were enormously successful, and spread spectrum took off. That was 2 years after his PhD. He already established a whole new technology of spread spectrum, which, as we know, is still a dominant technology today. In his thesis, he solved a piece of that problem, which was an unsolved problem, basically how to generate the same noise-like waveform at two different locations. Now, today it's easy. We understand about pseudo-noise generators. That time it was not, but he had some crypto experience, understood key sequences, and out of that came the brilliant idea of creating spread spectrum. The way they synchronized the two systems was very simple. The transmitter would transmit a tone, a small burst tone on a known frequency, and the receiver was just listening on that frequency. Once it got it, it started generating sequence. The Davenport I'm talking about there is the famous Davenport who wrote the book Davenport and Root, which I expect none of you have ever heard of. It was a classic book. Jack, you know about it. It's a classic book in the 60s on basically detection and communications. After that success, a gentleman by the name of Bob Price appeared on the scene, who had been a member of their group to begin with. Now, in developing the spread spectrum system, they found they were subject to multipath, to which we're still subject. And as Paul put it, you take a problem which you can't fix, and when you can't fix it, you feature it. I think this was an IBM slogan one time. And the fix, or the feature, was how to take advantage of these many copies of the same signal coming in, slightly delayed in time, and put them together. And out of that came, basically, the rake receiver design, which again was an enormous innovation in the days when reception of weak signals was important. And we still continue to see rake receivers today. Basically, he was interested in optimizing the signal-to-noise ratio of the signal, whereas one of our future distinguished lecturers, Bob Luckey, was concerned with the problem of minimizing intersymbol interference through something called an adaptive equalizer, which revolutionized data communications in the telephone system. Well, it's the same idea, but to optimize, if you will, signal-to-noise ratio. So that's two. Three, Paul then went into radar astronomy. Again, something that Lincoln Laboratory was involved with. And he decided he'd like to know what's happening on Venus. Venus was a planet hidden with clouds, and nobody knew what shape it was internally or which way it was rotating. So we developed the ability to basically match Doppler and range radar signals to identify the rotation, orientation, and the rotation axes, as well as some of the planet features. After that, he went into seismology. Now, the people who were basically studying seismic operations and exploring, for example, for oil fields, were using explosive charges, and the distance between the explosive charges was small compared to the wavelength of the propagating wave. As any good radio engineer knows, you don't do that. You've got to have receivers and transmitters which are a significant fraction of the wavelength. Out of that came array receivers. Again, a whole field that permeated for at least 20 years. At this point, in the 60s, Paul felt a kind of frustration working for a military organization, Lincoln Laboratory, and so he went to a very commercial organization, the three-letter organization IBM. He went to Yorktown and started to do management in communications. It was a major, major career change. And so Paul recognized he had to re-educate himself, and he did. And he started re-educating himself on data communications. And out of that came the beginnings of peer-to-peer communications, which IBM then continued to develop. And out of that came the APPN system, which of course is the IBM networking architecture of today, whereas at that time was a host-centric architecture. Today it's peer-to-peer. So again, a sweeping development that originated in Paul's head. Paul then went on to Armonk to work on the corporate staff with Lou Branscombe. He came back to Yorktown in '83 when APPN was an enormous success, and he got interested in yet another topic, wavelength division multiplexing in fiber optics, the topic for today's talk. So let's count them. Spread spectrum, rake receivers, radar astronomy, seismic arrays, and finally now APPN and wavelength division multiplexing. Not a small set of very significant. Any one of us be thrilled to any single one of those in the entire career. Paul's had a long succession of these. So what is it that he can tell you that helped him achieve this sequence of successes? It's a very simple idea, one you've heard before, but in which he's a perfect example. You have to learn how to learn. You're going to change your careers very likely a half dozen times in your 30 years of professional life. If you can't adapt along the way, if you learn how to learn rather than learn a particular technology and only understand the details of today's state of the art, you're not going to make it. You've got to be adaptive and learn here at the university in your own head how to adapt. So today Paul's going to talk to us about his latest success area, wavelength division multiplexing, the key to openness.
Thank you, man. Where shall I? Well, I'd like to range over a variety of kinds of ideas, ranging from the philosophical questions of what do our fearless leaders in Washington really mean by providing us an information infrastructure that's truly universal, all the way to how do you solve the specific technology problem of radiating light at a narrow range of optical frequencies and do so at low cost and high volume and great reliability. And what kind of systems do you build once you've developed such a set of ideas? So here's the title of my talk. I want to talk about something called all-optical networks, and I want to describe why a number of the practitioners, and there are many around the world, of this set of ideas think that this kind of networking is the key to universal service or openness or whatever you want to call it. Whatever you want to call it, I think will be clear in the next couple of slides. Let's go back, come with me down memory lane to 1934, when they set up something called the FCC. There's a thing called the Communication Act of 1934, the tangible consequence of which was the formation of the Federal Communications Commission. But the principles upon which that was made to happen, there should be a knob here for this thing. Reverse. Well, okay. So what the FCC was empowered to do was to provide to everybody in the U.S. something called universal service. That is, anybody should be able to get telephone service, no matter how poor they were or where they were. And in the radio communication case, it meant that the spectrum, which was regarded as a public resource, should be managed in an altruistic way. And in the case of the other big communication area, wire communication, that too should be managed in such a way that it redounded to the maximum benefit of everybody. Now that issue was never really clearly resolved until the 1970s, when a series of court cases produced the world that we have today, where public access to copper as the transmission medium was made the law of the land. And maybe some of you remember these court battles and remember that at one point you couldn't get free access to the bare copper medium. You had to go through a restricted set of companies and only they could provide you this kind of access. Now we have all kinds of benefits that have accrued from this free access: Radio Shack, modems, fax machines. The internet is probably the best example of what kind of innovation is unleashed when you provide free access to one of these technologies. In March 1993, there was an important event that made no headlines, but it will be looked upon as a headline event when the history of telecommunications is written. There was a ruling that said that fiber optics is just wires in the sense of the Act of 1934, and that therefore it too must be made freely available to the public for all kinds of direct access to the fiber. The jargon term that's used in the biz is dark fiber. That is, if it doesn't have previous traffic on it that's been committed in some specific format or specific ownership. It's unlit, it's therefore dark, it's therefore free to be attached to in any way the subscriber wants. Now, at the same time, we can talk sort of geopolitically about something called universal access and speak the language of the Washington lawyers while we're doing it. There's also another set of words that network architects know called openness. Here we go. This is, I've heard this term used by marketing people, but also by especially colleagues of ours in the network architecture business. And what openness means is that you should be able to attach to the other person that you want to communicate with the maximum amount of freedom. You shouldn't be the victim of proprietary undocumented protocols, of bandwidth limitations, of certain ways of handling bit patterns. Optimally, what openness means is that you should be able to communicate with that partner with minimum interference from any third party. So, for example, you'd rather not have anybody tell you that the medium that you have has got only 3.5 kilohertz of bandwidth because it's copper, and therefore there's a maximum bit rate you can use. And if you want to squeeze 14.4 kilobits through that you better do trellis coding and suffer the complexities and the delays and so forth, and that sort of stuff. You'd like to have protocol openness or protocol transparency, as they call it, in that you would like to be able to use whatever bit rate, framing convention, and so forth you and your partner decide you'd like to use without having to obey the dictates of an intervening third party called the network. There's also questions of topological freedoms. That is, you'd like to be able to go plug into this thing any place that you can. And the classic example of heroic achievement in that respect is the copper-based telephone company. You'd also like to be able to add and move and change where your end user locations are with maximum freedom. And so let's call this topological openness. And finally, you'd like this is not so much a problem for private users, but for corporate users, it's an enormous problem. That if you're betting your business on some big network, then somehow somebody has got to do the job of problem determination, recovery, change management, and all that sort of stuff of that network, that third party that you're going through. And this has gotten extremely complex today because of intervening technology that lies between you at your PC, for example, and some other person at his PC. That system in between is enormously complex. So if you want to achieve the utopian datum or the maximum possible openness, so-called, you would like to have something that doesn't care what the bit rate is, doesn't care what the protocol is, except that the two parties conversing should obey each other's protocol, is extremely flexible as to where it is and where it can be changed to be. And you like it to be simple so that it doesn't have thousands of possible failure modes in the middle, but maybe just 2 or 3. Well, I want to plead the case today that fiber optic technology will give you that. And remember this slide, because I'm going to come back to it at the end after I've gone through a lot of other stuff and try to make the claim that point by point, the kind of network that I'm going to talk about, all-optical networks, will in fact do this. Now, the thing, I should give you a little bit of a preview by saying the thing that we aren't able to do today with all-optical networks that appears on this list is the third one from the bottom. We don't have pervasive endpoints, but we're going to have them because fiber to the home and fiber to the business is simply a matter of time and economics, and it's rapidly becoming available. So we just have to wait for that. Let's distinguish between 3 generations of what the physical basis of the networks that we know today are. The first generation is the pre-fiber generation, and it's not all that ancient either. Internet is based on voice grid telephone connections into your local computer. T-carrier is something based on the use of copper. Token rings and Ethernets for local area networks are all took no cognizance of the availability of fiber optic technology. What we think of as really exotic high-speed networks today, the latest gee whiz thing that does use fiber, uses it as a direct one-for-one replacement of copper with minor changes in the architecture. For example, FDDI, fiber digital data interface, is nothing more than an old-time token ring with a few band-aids put on the architecture and the bit rate elevated to 100 megabits, and that's all it is. SONET, where the O stands for optical, synchronous optical network, is today's version of old-time T-carrier. And these national gigabit test beds, such as the ones that you folks are involved in, are based on using fiber optics as the medium of preference for long-distance communication. But there's nothing different in the way the network is constructed from its predecessors that were based on copper. Now, the third generation is the one that I want to talk about. It's the idea of going back and taking a look at fiber and seeing what is it that's unique about it, and asking yourself, when you find something unique about it, is that the solution to no known problem? Is it just a solution in search of a problem? Or is it the answer to something? And the whole message of this talk is that the unique properties of fiber are, in fact, the answer to this challenge of openness that I had in the last slide. An all-optical network, I finally get around to defining what I mean by that term, is a network in which, between the end users, once the path between me as a logical entity and, say, some program at the other end as another logical entity, once that path goes from electrical to optical, it never becomes electrical again until it gets to the node at the other end, where it becomes electrical again and then becomes logical. So an all-optical network is any assemblage of light pads, you might call them, that remain all optical as they thread their way through the network between the two end nodes. Now, the first thing that attracted people to this, the first unique property of fiber was its humongous bandwidth. I mean, here's a picture of the attenuation of any silica medium as a function of the optical wavelength transmitted through it. This applies to a chunk of it in your hand, or single mode fiber, or multi-mode fiber, or anything. The attenuation as a function of wavelength falls off with a Rayleigh scattering, so-called, and runs into a rock wall at the long wavelength end called the infrared absorption band. But in between there's a trough, which when you look at it as a physicist looks fairly narrow. But if you look at it as a communication engineer, you say, hey, this 200 nanometers or 0.2 of a micron wavelength is in fact 25 beautiful 1,000 gigahertz. Now, just reflect on that number a minute. 25,000 gigahertz is approximately the bit rate, the accommodated bit rate of every telephone call in the US going on simultaneously over one fiber at the peak busy hour of the year, which happens to be a certain hour on Mother's Day. It happens that this 25,000 gigahertz is also, as many of you probably recognize, about 3 orders of magnitude greater than the capability of the Earth's atmosphere to support radio communication. Ka band, about 40 gigahertz, is about as much as we can get through the atmosphere without running into oxygen absorption. So here we got a medium with 1,000 times that bandwidth, and it's all ours. We don't have, if you own a fiber from here to there. You don't have to talk to the FCC about using it. You don't have to worry about interfering with anybody else. It's all yours. So that's the thing that first attracted people about fiber, the uniqueness of it. The attenuation is so low, about 0.2 of a dB at that minimum thing, that you can go great distances before you ever need any repeater. So the attenuation is low, the bandwidth is humongous, as I said, and if you do the numbers, this 25,000 gigahertz is about 10, would you believe it, orders of magnitude greater than 3.5 kilohertz, which is what the 22 gauge copper that we know and love so well has for its bandwidth. Then there's another consequence of the basic physical principle that moving electrons, like for example ground loops and hum pickup and impulse noise and all that sort of stuff, will interact with the electrons that are carrying your message. Whereas photons moving don't see each other, which then means that there's absolutely no interference between photons at different wavelengths. It means that unless you deliberately leak some noise-like light into the fiber, you don't have any noise, any additive noise to deal with. And that means that you can just keep driving the error rate down just by cranking up the transmit power, cranking down the photoelectric receiver threshold sensitivity. Just keep doing that. You don't run into these situations that you have with electrical communication where you have to strive heroically on voice-grade telephone line to get the bit error rate down and it can lower to about 10 to the minus fifth or sixth. So let's say 10 orders of magnitude lower error rate. And the thing that's kind of chastening about this animal here, this fiber optic technology is, poof, there goes 50 years of information theory up the zoo. Because, I mean, look, it's, why worry about coding when you've got all this bandwidth? And if you want more or equalization, if you want a better error probability, just crank up the link budget a little bit. In the hills of North Carolina, where I was raised, in the wintertime, when it gets very, very cold, there's a saying that all you got to do if you want to get warm is just pull up another dog. Well, here, if you don't have enough link budgets, just you put a few more dBs of transmit power and you get whatever bit rate you want. Okay. I thought it was kind of funny, actually. So so bit rate, the achievable bandwidth, is the thing that first attracted people to this. And here's the famous, infamous accusation that's hurled against the classical way of doing communication that the aficionados of fiber optics in communication tend to throw. They speak of something called the electronic bottleneck, or more properly, the time division bottleneck. The idea is this, that for the last 50 years, we've built all of our networks on the basis of the idea that interleaving things in time was the way to go. And this has served us very, very well. Everything that we all know as far as networking is concerned is done that way. From the first teletype systems that were put on party lines, probably in the 40s sometime, to today's gigabit test beds and even more exotic things. Everything is done time division. Here's a toy example. If we wanted today to have 1,000 workstations, even though they ran at a megabit each and we're running 100% duty cycle, we could do that because we can go out to the Radio Shack or someplace and buy 1 gigabit technology, and we can have a little bit of 1 gigabit technology in the front end of every one of those workstations. And that technology is fast enough to keep up with the aggregate bit rate of all these workstations, which is 1,000 times 1 megabit, i.e. 1 gigabit. And by time interleaving, each node can watch all the bits go by and use only the ones that belong to it. Well, that's fine. And if you happen to be doing this optically, nobody ever told you, but you happen to be using one little tiny, almost invisible slice of the 25,000 gigahertz that are available. But what happens when somebody comes in with a wheelbarrow in the dead of night and replaces all of these 1 megabit workstations with 1 gigabit workstations? Alfonso and I were talking today about the medical image environment, which is coming on fast with extremely high resolution, high life-threatening sensitivity kinds of scenarios, and very urgent needs to transmit gigabits per second from one place to another right now. And there are a lot of other applications you can think of. Multimedia, teleconferencing is another, supercomputer interconnection is another, and they're just coming. And what happens if every one of your 1,000 nodes here wants to talk at 1 gigabit? Where are you going to get the technology to handle in the time-honored, old-time division way 1,000 gigabits? You're not going to. And one of the most promising ways of dealing with that is simply to go back and look at what the optical spectrum is. And notice that you've got all of those humongous gigabits per second. And therefore, what you would be tempted to do is to use different colors of light, different wavelengths, for different optical connections. And that's the preferred mechanism of building these fiber optic networks. It turns out that if you use wavelength division, let's call it frequency division or wavelength division, it doesn't matter, it's very simple because each node only has to run at its own native bit rate. It doesn't have to look at all the other bits. You could conceivably use code division, or you could conceivably use optical time division. But basically, wavelength division is just so simple and so obvious and direct that that's the one that these many groups around the world that I spoke of are using. Now, the second big reason for wanting to use the fiber optic medium goes to this question of protocol openness that I mentioned. Those who have thought about the question of protocol heterogeneity realize that in real networks you have a huge problem. There is no such thing that I've ever heard of as an all IBM commercial network or an all DEC. There's no company that I've ever heard of who has only IBM networking or only DEC networking or only ISDN or only internet. It's a zoo out there, and it's getting worse. Every once in a while a panacea comes along, like OSI was a few years ago. That was the favorite. That was going to wipe everybody else out, right? Everybody was going to throw away millions of dollars worth of existing code and adopt this new thing called OSI and live happily ever after. There was no such thing as technological innovation causing new ideas to come along. So it would be permanent and static and utopian. Somewhat the same flavor is being heard in the land today with regard to ATM. It too will come and it too will go. The fact of the matter is that there's a Murphy's Law of protocols, or call it the protocol zoo. And every animal in the protocol zoo is immortal. There is a lot of bisync out there. If you don't believe they're immortal, you know what ASCII is. There were a lot of people who thought ASCII was dead about 12 years ago, and then along came the PCs. There's more ASCII in the world than anything else today. At any rate, there is this heterogeneity or protocol zoo problem out there, and it's not just academic. It is a first-order problem with any real network owner in the world. And there are three well-known ways of getting around it. The first one, which we've already mentioned, is to say, well, I've come up with a new protocol that's so utopian and so perfect that everybody should converge to it. We know that isn't going to work. The other thing is to geographically partition everything in your company into different little universes or sub-networks, all of which talk uniformly the same convention within that island, and then you connect the islands together with protocol converters. And that's done. But that's pretty clumsy, It's expensive, big performance hits. It's not the way to go. The way it seems to work, and we don't really realize, but we've had this for almost 100 years now with the telephone company, is the transparency that's granted by plain old-fashioned circuit switching. Take the 22 gauge copper that I was throwing fruit at a minute ago. Take the fact that you have a protocol dependency between your telephone and the network that's only transitory. You make a connection, and then it comes again when you have to hang up. You go on hook again, and there's another protocol that executes. But between those two, there is this juicy period of time when you can send anything you want. And it's the transparency of this interval. It says I can send anything I want as long as I don't exceed 3.5 kilohertz and 50 volts. If I don't electrocute somebody or send stuff that's going to not get there because it doesn't go within the passband, I can send Radio Shack modems, answering machines, fax machines, internet bits, anything I want. And now, during this interval here, we have what we wanted. The issue is the protocol agreements between the two end players without any agreement being imposed by the network in the middle. Well, so those are the big grabbers about these so-called all-optical networks. That if you can keep the path optical from end to end, and you can divide up this spectrum of 25,000 gigahertz into little slices and send each of your connections across a different little slice, you can get a lot of bits through, because 25,000 gigahertz is just this gigantic number. And secondly, you can have different protocols on different wavelengths. So now let me zoom in a little more. An all-optical network is one which has a continuous light path from end to end. And a light path I'm going to define as a topological series of edges qualified by a wavelength. That is, it's a geographical description coupled with a label, which is what wavelength are you using. You could have the same zigzag path through the network running at a different wavelength, and that'd be a different light path. Or you could have that same wavelength going over some other zigzag path, that would be a different light path. So a light path is defined as a pair of a route, and the other member of the pair is the wavelength used on that route. As I said before, there's no optical electronic conversion on route, and it should be fairly obvious that there's no way you can intervene and store these bits and process them and buffer them. Once you launch the bit into that light path, it's gone. And it goes to the other end at the speed of a gossamer wing, it gets there. And there's nothing you can do to it in the meantime to buffer it or process it or store it. And there are people who are working on exotic technologies that someday may allow you to buffer and store it, but as in the foreseeable future, you really can't do that. The usual choices I've mentioned is wavelength division, and that if you use circuit switching, dedicate a path throughout the time that you want to use it as a circuit switch connection, then you preserve a protocol transparency. You can set any bit pattern, any packet convention you want. And it keeps the bit rate per node low, as I mentioned. And now I want to zoom in a little more and say that there are two species of these networks. There's the kind that people have built so far called broadcast and select networks, and the kind that people are just now beginning to speculate about building, which are called wavelength routing networks. Here is what a broadcast and select network looks like. There is a network in the middle composed entirely of glass. That is, you can imagine that there's a sort of an ellipse that encloses all of these fibers indicated by the black lines and these blue things, which are just passive couplers and splitters. And I've shown it as a bunch of these couplers and splitters rather than just one in the middle, because it's often in real networks of all types desirable to regionalize it. That is, to have clusters, like there's one cluster in in this building, there's another cluster in the building next door. Maybe there's enough that there's one cluster in this floor and another cluster upstairs. Real practical networks come in groups. And therefore, it's better to show this diagram as having these sub-optical splitters and combiners rather than to fake it out and say that they always consist of a single thing in the middle. The effect is the same, that if this guy here wants to communicate with that one, and he sends a message on lambda 1 because he's number 1 and lambda number, way color of light lambda 1 is assigned to him, then it gets broadcast to everybody by means of these blue things. And that's why they call it a broadcast and select network. The good news is that it's broadcast to everybody. The bad news is it's broadcast to everybody. That is, by broadcasting it to everybody, all you got to do is to have a tunable receiver in each node, and by tuning that receiver, you can get that transmission. The bad news is that you've wasted your power on all but one of the receivers. You begin to smell that this is nothing more or less than old-time radio. That you know, you've got your car phone, and you're broadcasting to everybody, and only one who, 10 to the minus 10th, or who knows how little, but that energy finally enters the car phone of the person you're talking to, or the phone of the person you're talking to. It's just radio. Each one of these stations has an assigned transmit frequency, and every receiver is tunable. The network in the middle is glass, which means it is cheap. It has almost no failure modes. It has, it's unpowered. It's part of its having almost no failure modes. It's capable of being made with lithography, so it can be extremely simple and even cheaper than they are today. And it's just in all respects similar to the Earth's propagation medium. You just send this message in and everybody hears it. There's a protocol that executes. Let me, I got this diagram on the board. Let me just tell you the protocol that we implemented to set up one of these light pads, which is shown by this yellow line there, if you can see the yellow. What we did was, suppose node number 1 wants to talk to node number 2. If node number 2 is already busy, you have to wait. But the way the protocol works is this. The minute port number 1 decides that he wants to talk to number 2, he starts issuing call requests that are qualified with the address 2. The minute number 2 becomes unbusy, he is supposed to do a search up and down the entire band of these frequencies until he comes across a node that has not only a call request active on it, but that the call request is calling for him. The minute he detects 3 or 4 successive occurrences of that, he throws a bit that freezes this tunable receiver to that wavelength through an AFC loop, automatic frequency control loop, just like you have in your car radio. And this guy immediately starts issuing call requests to that one. That guy locks in, and now they have a full duplex link. That all takes about 10 milliseconds in the network that we built 2 years ago called Rainbow 1, which we field tested over in Europe and now have installed at the research division in Westchester County. You can't, again, yellow lines, sorry about that. This bunch of nodes here are at a place called Hawthorne 2, which is a big building, one of the research division buildings in Hawthorne, New York. And right next to that is another building called Hawthorne 1, strangely enough, which has these nodes in it. And then 25 kilometers away, as the fiber flies, is the Yorktown building with still another node. Now, every one of these nodes is implemented as a circuit card, just a plug-in card that goes as a standard PC PS2 plug-in card that goes into the system bus, which IBM calls for some reason lost to the memory of man, a microchannel. And Anyhow, this micro channel you can stick these different cards into it. And so we implemented this Rainbow One network as a bunch of components on one of those cards. And we have half a dozen or so of these PS2-like machines scattered around Westchester County with these plug-in cards in them, each of them being a node that has a little laser that transmits on its own assigned frequency of light, like the radio station, and each of which has a tunable receiver, which, depending on what voltage you put across the two pins, will take up some particular optical frequency to receive on. And it executes this protocol. If I have my demo point up there, which happens to be in my office, if anyone want to come by and see it, and I hit a key on that PS2 that says, I hit Y for Yorktown, what happens is it starts issuing call requests that he wants to talk to Yorktown, and meantime the tunable receiver up there at Yorktown is tuning around, stumbles across my call request, it locks into my wavelength, and then sends call requests to me, and I lock in on its wavelength, and now we have this full duplex connection, and I can watch the 270 megabit video that's emanated at Yorktown. And this is a very practical thing, because one day we got a call from the security guards that, is that your camera? Yeah, who's calling? Was it active on such a day? Yes, who's this? Was it pointed out at the parking lot? Yeah, who is this? And finally we learned there'd been a car theft or something out in the parking lot, and they saw our camera and wondered if it was on. So, very practical network in this real world. So that's Rainbow One. Other people have realized these broadcast and select networks. Ours, we think, is kind of the leading realization in being almost commercially useful. It exists on a single oversized PS2 card. It looks sort of like this. A lot of electronic chips on it to provide the interface to the microchannel. The search protocol that I just described is on a bunch of other chips. Almost everything on this board, as far as the real estate is concerned, is electrical. Very great complexity. You know how much is on a chip these days. So most of the square footage, square inchage on this board is electronic. And over in the corner is about 25% of the real estate, but about 85% of the cost. And that's the photonic stuff. There's a little laser about the size of a sugar cube. It sends its data out into the glass network. It comes back on another fiber and enters this tunable filter, which only costs $7,000. And it enters into a photodetector, which only costs $1,500. And here the filter servo circuits, which being electronic probably cost 50 cents. And then this thing locks it in when it's detected the call request. Now the lesson of these numbers that I'm throwing away with a style calculated to make you laugh are actually no joke. And that's why this thing, when mentioned to our product developers in IBM, has stirred up a tremendous amount of apathy. The bag of parts cost for this thing is 16 American dollars, of which 11,000 is in the functionally almost trivially simple part of it, namely the photonics. And the electronics, which is quite complex, is the rest of it. And that seems to be the rule these days. The electronics is dirt cheap, and it can be made extremely complicated so far, and the photonics is just beginning to climb up the learning curve that LSI Electronics has had now for 25 years. So we figure, and I'll get to this later on, that maybe we should try to climb up that same learning curve using lithography. And maybe these filters that cost $7,000 will cost $7. And the laser, which I didn't say, that costs about $4,000 today. Maybe that'll cost $4 if we're clever enough. here is an overview on one chart of the program of my group at IBM Research. The first thing we did was to do an experiment back in 1988, which has now become a quasi-product called MuxMaster. That experiment was not a fancy network. In fact, it was so simple that we didn't think anybody had any use for it, and we never even wrote it up. It certainly wouldn't qualify as an acceptable article in any respectable journal because there really wasn't anything new about it. It was just meat and potatoes. What we did was to take two units called gratings, G-R-A-T-I-N-G-S, which are like a prism, except they have fibers sticking out of them rather than you look at it. It's got 20 fibers differentiated by different wavelengths and one common fiber. Now suppose you use this thing totally as a multiplexer. What that says is this grating thing, if you put into fiber pigtail number 1, lambda 1, and only if you use lambda 1 or something very close to it, will that bit stream, that color of light, appear on the output fiber. If you use put number 2 then on wavelength number 2, it will appear on the output fiber. So by putting up to 20 of these, you can use this as a 20 to 1 multiplexer. When we told people we've got a 20 to 1 multiplexer in the lab, it's about that long and about that square and doesn't need any power. They say, well, that can't be. Last time I saw a 20 to 1 multiplexer was 6 feet of rack electronic equipment. But here's this little thing, passive, that would multiplex 20 wavelengths and require no power. And you could use the same thing for demultiplexing. Well, what we did was to use 10 of the wavelengths to go from this way to this way, and the other 10 to go from here to here. That meant that you could use one single mode fiber, and by the way, it's 50 kilometers long between those two. So we could use one 50 kilometer fiber to send 10 full duplex channels, and nobody cared what each protocol was. The bandwidth of each one of those channels was 10 gigahertz. So recently, we found that this is a very important thing to have. It might even be useful between here and Caltech, for example, because you can take one bare fiber, instead of spending $150 per mile per month per strand for 20 strands of fiber, you spend that for one fiber, and you've got all of these different channels going over that fiber. We revived that, as I said, in 1993, and we're trying to make something out of it called MuxMaster. Meantime, as I mentioned, in 1991, we had Rainbow 1, which just used ECL voltage level inputs with circuit switch, and maximum speed was a third of a gigabit per node, 32 nodes. We are working with Los Alamos Lab under DOE sponsorship to develop a thing which should be ready for Supercomputer 92, 94 this fall, a big show in Washington, called Rainbow 2, which is likewise circuit switch, but talks a gigabit each of 32 nodes, and is specifically made for HIPPE, high performance parallel interface, and also has almost complete offload into the Rainbow 2 node of most of the path length of TCP/IP, so that your supercomputer doesn't have to use its cycles to execute the upper layers of TCP/IP. They've done for it in the outboard box, the Rainbow 2 node, which is not a printed circuit card as it was in Rainbow 1, but it's a box, an external modem, if you want to call it that. Rainbow 3 is a dream. It's packet switched, which we think we know exactly how to do. We know the protocols, but we don't have the technology to switch in sub-microsecond times yet. The tunable filter that's in Rainbow 2 takes about 5 milliseconds to tune, and so we have to do circuit switching. We lose too many bits if we tried to make one packet and then retune this and another packet and then retune. But if we get sub-microsecond packet switching, we can do optical packet switching. So that's what we planned with Rainbow 3, which is just a dream in our eye. Here is the second kind of network, wavelength routing networks. This is the thing that ARPA is putting so much money into. We have been working on this under ARPA sponsorship, and the dream there is to have highly scalable networks. Meaning that you can keep adding more and more nodes without exhausting your wavelengths nearly as rapidly as you would with the broadcast and select network. The advantage of broadcast and select networks is that you can go out and build them today. You can go out on the street and get these tunable filters and these other things, and you can actually build them, and we did it, and other people have done it. But the disadvantages, as you may have recognized, is that it not only throws most of the power away by sending it to nodes that don't want it, but it also depletes the pool of wavelengths that you've got available. If you want half-duplex ports, you've only got 64 wavelengths. The number of nodes you're going to be able to support is 32. So, no, I'm sorry. Yeah, no, with the one that we have, it would be 32. It's not half the number of waves, equal to the number of waves. For 801, if we got 32 nodes, 32 wavelengths, we can support 32 nodes. Now, a wavelength routing network, as you might suspect from the way I've sort of set you up with this, doesn't broadcast the energy to all the nodes. It deliberately steers it by a very clever method called wavelength routing, so that if I emit something into the network at one particular wavelength, it never gets broadcast to everybody, but instead gets steered in a zigzag path so that the light will always stay at my wavelength, but it will never get scattered to other people. It will wend its way through the network following a fixed path, and since it isn't throwing its energy out into other unwanted exits from individual nodes that it comes across along the path, there is no wastage of power by that. And also, it's obvious that if I keep these things out of each other's way, I can reuse the wavelength. That is, I could have, again yellow, I hope you can see it, there is a light path that goes along this funny path. That lambda 1 travels here and only exits from this one, doesn't go anywhere else. And when it hits that node, it only exits from that one, and in that way it's steered all the way to this place. At the meantime, lambda number 9, for example, might be sending energy along the reverse path to here. But while that's going on, here's somebody else over here using lambda 9 for something else to go from here to here to here to here. So now what you have to do is that you have to make the central glass network switchable. There's a penalty for this. You have to provide each port with 2 transmitters, with a tunable transmitter and a tunable receiver for each port, and each light path then requires 2, one at each end. This is a slight history. The central glass network now has to be switchable unless you want to have frozen light paths, which is not doesn't offer you much promise in increasing capacity and responding to dynamic network changes. So what each of these blue things does is to vector each incoming wavelength on a given input port to some other port. Up in the upper left, lambda 1 coming in on some other port would be vectored to some other output port. So in general, every one of these fibers can have all of the wavelengths traveling on it. But what happens to those wavelengths as it enters a node is that they suffer different redirections within the node. Now these networks are just beginning to be understood, and here is what one of these wavelength routers might look like as a technology. Going back again to this grating that I mentioned. Here is a 2x2 wavelength router. The number of ports is P, which is 2 in this illustration. The number of wavelengths is W. Now, what happens is the grating, take this port here. Light comes in at all W of these wavelengths and is spread out into exit ports, W of them. And for each of these W exit ports, there is a plane in which there's a P by P switch, 2 by 2 in this case. Here's the other grating for the other input port. And either this switch is going to take lambda 1 here and send it to that output port, or it's going to send it to this output. There are no other choices. And that choice is made by electrically actuating this plane with a single binary bit. If you had 3 ports, or say suppose you had 4 ports, then it would be a 2-bit word that would have to actuate this plane, and this would be a 4 by 4 switch. But anyhow, you see how this thing works. You have a digital word supplied plane by plane equal bit by bit, or whatever the degree of freedom of that plane is, as you go down that word, and that this thing should say word instead of work. Word. And so this is how people are actively at work trying to make these things. And the way people are thinking of doing this is to do it by lithography, which looks like a pretty good deal. Now it turns out that the number of wavelengths is very crucial for all of these networks. As I have pointed out, in a broadcast and select network, you're totally limited in the number of ports you can have by how large your pool of wavelengths is. With wavelength routing networks, you've expanded things. You've been able to reuse the same wavelength many places in the network at the same time. And here's some hot off the press simulation data on some randomly chosen networks of dimension up to 100 nodes. That work will be extended to 1,000 nodes. But by guesstimating where this line seems to trend, it sort of says that if, for example, we were to have a 1,000 node wavelength routing network, and we had W wavelengths, then we would have 50 W possible connections in that network. So if, and I'll be showing you next a technology we're using to try to get 128 wavelengths, so that means you would have 50 times 128, or about 6,000 possible connections you could have between your 1,000 nodes, which is going to be quite useful. Here's that technology. This is almost the last slide. For those of you that feel that I've talked too long. This is a chipset, an optoelectronic chipset we're trying to develop. The idea here is that there's a common optical component and common optical component and one of 4 electronic components depending on what you want to do. Let's suppose you want to build a tunable receiver. What you would do if you want to build a tunable receiver is use this common thing and this guy. If you wanted to build a tunable transmitter, you'd use this common thing and that guy. And now let me go through it. What happens is that light comes in this fiber, which is butt coupled into this little optical club sandwich, and there is a layer in this club sandwich that propagates the light. The light fans out in a natural radiation pattern from the end of that fiber. It hits a grating, again a grating. Grating is something for which the takeoff angle depends on the wavelength. That's the definition of a grating. So here comes light with a whole lot of wavelengths, and it hits this grating. And being a grating, the takeoff angle is going to depend on the wavelength, so that different channels will come off that grating at a different angle. Now this grating is curved so that it refocuses the light back again. And what happens is the light hits this 45-degree mirror, and channel number 1 hits the 45-degree mirror here, number 2 there, number 3 there, and number 128 way over here. It hits the 45-degree mirror, bounces down, and maybe you see what's going to happen. You have glued up to next to this one with Elmer's glue or something. This probably epoxy. I don't know. Rejected anyway. Something. Sorry. You take this thing, which is in our present realization is gallium arsenide, and you glue it right up against this thing so that the light coming off of channel 1 falls on photodetector number 1, and that from light number 2 falls on photodetector number 2, and so forth. And then if you want a tunable receiver, you simply follow this with a switching, amplifying, and special low noise whiz-bang electronics that select one of these and route it to the output. We've already built one of these with 32 channels, and we're trying to build one with 128. This looks like a nice, cheap, economical way to go to build a 128 channel tunable receiver. Because all you got to do is to feed your digital word into this selection network and pick whichever one of the 128 wavelengths you want to receive, and you got it. And since it's lithographically made instead of handcrafted by very practiced artisans, as the technology today is, it should be capable of mass production and good cost production. Now, if you want to build a 120 element link, suppose you wanted to link Caltech with UCLA, and you didn't want 20 channels like this thing that I showed before, you wanted 128 channels, then what you would do would be you would just amplify all of these 128 outputs and feed these detected signals from the photodetector. You just use all of them instead of switching only one of them to the output. So much for receiving end. But how about the transmitter? How do you avoid buying 128 $4,000 lasers, each one at different wavelengths? Well, we didn't know how to do that until we read about some ideas in England. A laser is simply a piece of stuff. Indium phosphide, in our case. Pretty exotic stuff. And it's a little piece about the size of a grain of salt. Unbelievable technology, this. This little cubic thing, which can cost several thousands of dollars, and it's like that size, it is made to laze by feeding pump current into it, so-called. And something called stimulated emission happens. These electrons get converted into photons. And it doesn't do much. It radiates in all directions, forming something called a LED, such as you have on your calculator, unless by chance you put two mirrors on opposite edges of that little cube of salt. Now the light is trapped between these two mirrors and accentuates and resonates, builds up to huge proportions. They all fall in lockstep with one another, and you get milliwatts of power out of this tiny little sugar cube. So the condition is to have the so-called active region, this piece of crud, stuff, I guess I called it, indium phosphide, with a mirror on the back end of it. Now, if I pump this thing and I have a mirror on the front of it, it's going to laze all over the place in frequency. But suppose I anti-reflection coat that thing, glue this one up against this one with my Elmer's glue, and see to it that there's no other reflections between this mirror at the back of it and the butt end of that fiber, which I've sneakily added a reflective surface to, then what frequency do you think it's going to laze at? It will laze at only that frequency that survives a path between here and there. It's got to go through the grating to do that. And so it's going to laze very near the peak of that grating response, that tooth of the frequency response of that grating. So we think, fingers crossed, that once we get past getting our 120 element receiver, then we can build a 128 element transmitter, which could be made tunable by switching the pump current to one and only one of these lasers at a time, or we could drive all of them with independent bit streams and get our multiplexer. All of this being lithographical, and therefore a step down the same road that the computer chip went 20 years ago. You could think of it as the third coming of Gutenberg, okay? The first coming being those things that you guys have to spend so many evenings with that are horrible and come out of the library, books. The second coming of Gutenberg being the computer chip, the digital or analog LSI chip, and the third being what lithography will do for photonics. Okay, I promised to return to my chart to talk about openness. Again, that lovely yellow color. It's so easy to see. This is the very same chart you saw before, where the claim was made that all optical networks will sort of remove the limits on bit rate. And the reason for that, I think now I've justified that claim, is this enormous bandwidth that's available. I also predicted that you would find that perhaps a persuasive case had been made for protocol independence. And the use of circuit switching is my reason for saying that I think these networks will do that. Then I said that topological openness, the easy add, move, change business, was a factor of these networks. The reason that I say that's justified is that when you change one of these networks, you're changing almost nothing. It's not a big switch that you have to move from one place to another. For example, up in the corner of this building, if suddenly there's a reorganization in a place that had one Sun workstation, now you're going to put 32 workstations in that same room. With some kinds of networks, you would have to do a lot of rerouting of switches and radio paths from the simple switch, or token ring distributed distribution frames or whatever. In this case, you already have a fiber to that place. And you have another one coming back again. So all you got to do is to put the splitters and combiners that these networks require, and you've made that topological change. So the fact that the components are simple and passive, in most cases, they're certainly passive in the broadcast and select case, is the reason that I argue that all optical networks have this topological flexibility. And then the network management openness is a consequence of a very small number of possible failure modes that there might be in the middle of the network. Okay, so let's wind up by asking, why hasn't this already happened if it's all that wonderful? And the reason is that the component costs stir up a tremendous amount of apathy in the parts of anybody who has to take responsibility for developing and marketing products in this area. Lithography, it looks to us, will provide the solution by this third coming of Gutenberg which we enjoy. The number of wavelengths has got to go up. There's plenty of bandwidth there, but we think we can crank up the wavelengths to 128 with this lithography technology. But there's 25,000 gigahertz there to be played with, and as time goes on, we have to get that multiple up further by getting components that are stable and various wavelengths selected and easy to control. The other ingredient that I haven't really talked about is that the paths are got to be available in the first place for you to implement this network over. And as we were discussing at lunch a year ago, that was felt to be a big problem. But at this point, we're finding in talking to IBM customers who are interested in possibly installing these kinds of resources that is getting to be less of a problem because there's so much competition out there. I'll just flash this list. These are all the people, sort of in chronological order, who have been prototyping these networks. Okay, here's the very last. I keep saying I'm going to show the last chart. I bet you can believe I had a last chart. This is where I think we are. The issues, unlike just a few years ago, are pretty well understood. There are no revolutionary new inventions in either architecture or components at this point. Things have sort of leveled off. You've got to drive the cost down. You've got to make them stable. The Europeans have been in this longer than we have. They had sort of led the charge, but 2 years ago, ARPA got into it in a really big way. And first to the tune of about $15 million, and now they're in it again for about $70 million. Japan is catching up. They've been leaders in the components, but laggards in the system area. Now the Ministry of Post and Telecommunications is getting cranked up. And the overall point that I think is the valid way to come away from my talk with is that ATM is for sure going to be the next generation. These networks are simply not competitive with ATM as the generation that's about to happen. But sooner or later, like every other generation, that too will pass. Maybe it'll be 10 years from now or 6 years from now. This stuff I've talked about for the last too long is, I think, a pretty strong candidate for the basis of the infrastructure in the generation after that. Thank you.